Hello everyone. Now that we are done with limits, it's only logical that we continue our journey with continuity and differentiability. In fact, what is continuity? A limit. What is differentiability? Is still a limit. One can go further and ask, what is integrability? Is still a limit. What is area? Again, a limit. And finally, after all, what is calculus? A limit. So you see that the concept of limit is integral or say vital to the all of calculus. So now in this lecture today, I will start continuity and differentiability. And so without wasting any further time, let me just go and share the screen with you all. Let me just check there is some trouble. Sorry about that. Sorry about that. There was some technical problem. So let me begin my lecture. So just to give a quick recap, last time we discussed about the concept of limit. So let me just say that the definition was that once we want to find the limit of some function f at some point c, limit of f at c, then we need to be given the function defined in what is called a deleted neighborhood, which I'm writing NBD of C. It means if you want the limit of a function to be defined at C, then you must be given, or if you want to calculate the limit, if you want to calculate the limit of a function at C, then you need to be given the function defined in a deleted neighborhood of C. Now, it may also happen that f is defined at C, but that does not matter. So sometimes we say that let f be a function defined in the neighborhood of C except possibly, it's a technical phrase, except possibly at C itself. Means what you are saying is that let f be a function defined in the neighborhood of C except possibly at C itself. Means whether you give fc or u does not give fc, that does not matter. This does not matter. Means to calculate the limit of f at c, all I must be given is the definition of function in some neighborhood of c, rather deleted neighborhood of c. So this is the kind of notation we will use for this deleted neighborhood of c. Let's give the definition of continuity, that how we can use continuity now. So that definition says that let f be a function defined in some neighborhood of c. This time we are not saying deleted, means fc we do required. So let f c minus delta to c plus delta to r, f be this function. And if you want to calculate, or you want to find out that if f is continuous at c or not, you need to calculate limit of x tend to c f of c. If this limit x tend to c f of c, f of x, that equals f of c. Let me erase that. So if limit of x tends to c, f of x equals c, if this happens, f of c, then we can say that f is continuous at point c. The definition is quite simple, but it makes one thing clear, that limit must exist. Limit of fx at c must exist, means that both left hand limit, so limit x tend to c plus f of x, and limit x tend to c minus f of x, both must exist, means finite, and both must be equal, and also equal to f of c. So it's rather a combination of three things, that both right hand limit, this we call right hand limit, this we call left hand limit, and this is the value of the function at that point. So all these three numbers must exist, then only we can say that the limit of the function at c exists and function is continuous at c. If we go to the next definition, that is, suppose we want to define that what is meant by differentiability of f at c. For this, again it remains same, we must be given f in an open interval about c, that is c minus delta to c plus delta and to r, and we define that f prime c, that is derivative of f at c, is limit of h tends to 0, f of c plus h minus f of c over h, provided this limit, so if this limit exists. So this is provisional. This writing of this f prime c is provisional. We are saying that f prime c is equal to this limit if this limit exists. And the moment this limit exists, then f prime c is just the notation. It is the notation for differentiability of f at c. It is called derivative of f at c. So this is the kind of thing f prime c. Now, definition is quite simple. If I want to compare the three things, let me take a new color maybe. So say red. Suppose I want to compare how they match definition of limit, definition of continuity, and definition of differentiability. In fact, many students are not clear about the last two, continuity and differentiability. So for limit, you need to be given function f in c minus delta, c plus delta. You can subtract c from it. We don't need to r. For continuity, we need c minus delta, c plus delta to r. For differentiability, we need c minus delta, c plus delta to r. So condition for continuity and differentiability, what is required of function is same. That function must be defined in some neighborhood of C. While for limit, function must be defined in a neighborhood of C except possibly at C itself, means deleted neighborhood of C. And here fc need not be given. Fc, I don't care. It is given or not given. Here fc of course must be given. You see this domain includes C. Here also fc is of course given. Here we are finding limit of x tend to C f of x, and then comparing with value of f of C. If this equals, then this only is the telling that function is continuous at C. Here we are calculating some quotient, that is limit of h tend to 0 f of C plus h minus f of C over h. And if this limit exists, this only is the value of derivative at C, that is called f prime C. You must note that any limit calculation always have two parts, one left hand limit calculation and one right hand limit calculation. So let me take one example and let me insert some pages first. So the first example that I will take, it will be little more instructive, and it will tell you how you can use limit to calculate these expressions. So our first example is that we want to find out that f of x is given to be tan of tan x minus sine of sine x upon tan x minus sine x. It is defined like this, f of x. This is when x is not 0. And when x is 0, it is defined to be k. So consider this only in the neighborhood of 0. So x is not 0 and x is 0. Now this is like this defined. We are not bothered about this term being 0 or not, because we are just taking a neighborhood of 0. Now, your job is to find k such that f is continuous at origin, that is 0. So it's just a limit question. Continuity is just used in the first step. So I'll say that if f is continuous, then limit x tends to 0, f of x must be equal to f of 0, and that must equal k. So all is left to calculate limit x tend to 0 f of x. From the last 2 days, we have been doing this limit calculation. So we can calculate limit x tend to 0. Let's write tan of tan x minus sine of sine x over tan x minus sine x. Now we see that this form is of tan of alpha minus sine of some beta. So we can just expand. So we know tan of x, tan of theta, I'll write tan of theta is theta, or tan of, we can use x because there is no danger of this. So we can use the expansion tan of x is x minus x cubed by factorial 3, x plus, I'm sorry about that, this is just sine x. So we'll write sine x first. Sine x is x minus x cubed factorial 3, x factorial 5, and so on. When you do tan x, it is x plus x cubed over 3 and plus 2 over 15 x5. I need not term anything extra, so I will write here limit x tend to 0. Let me start here. It is going to take much more pace. Limit x tend to 0, tan of tan x. So tan of tan x, just put here tan x in place of x. we'll get tan of x plus tan cube x upon factorial 3 plus 2 by 15 tan 5x minus, if you do sine x, you will get sine x minus sine cube x upon factorial 3 plus sine 5x upon factorial 5 and all the way over tan x minus sine x. Here I want to make a little change. I would introduce something x cube and multiply x cube. The reason is that this limit we have calculated and we know easily. We know that tan x minus sine x over x cube, I can write like tan x times 1 minus cos x and whole upon x cube. So I can write again tan x over x times 1 minus cos x over x square. And that will simplify as 1. And 1 minus cos x upon x square, this limit will happen to be 1 over 2. Either you can get by L'Hopital or simple expansion. If you just differentiate once, you will get sine of x over 2x. This becomes 1, so 1 over 2. So this limit is 1 over 2. Means this is not a problem. This is taken care of. This whole thing becomes 1 over 2. So this comes out and this becomes 2 because it is the denominator. So 2 times limit x tend to 0. Then we have to figure out this one. We'll write tan x minus sine x. So again, we will write tan x minus sine x. Combine this term with this term. And then plus tan cube x upon factorial 3 and plus sine cube x. Tan cube x upon 3, not factorial 3. It is just 3, simple 3, as you can see here. So tan cube x upon 3 plus, or I may use a erasure. So this is tan cube x upon 3, and this also 3, and this is for sure factorial 3. This is plus sign upon x cube because 2 is here now. So 2 times, you again have tan x minus sine x over x cube, and plus, this is limit x tend to 0, and plus limit x tend to 0 tan cube x over 3x cube and plus sine cube x over 6x cube. So now this limit is 2 times this already we got. This was 1 by 2 plus this number is 1 over 3 and then 1 over 6. So we'll get 2 times 1 over 2 plus 1 over 2, and that is just 2 times 1 by 2. And so you will get the final answer as, this is 1 by 2, 1 by 2. So you should get the final answer as 2. So this is what my answer looks like. So this was an example of this one, that finding continuity or using continuity to find the value of k. The next example that I take would be much more instructive. So this is like this. This is one of the, it's rather one of the theorems. So you have to prove that if f is differentiable at C, implies f is continuous at C. This is a good proof, but still students often are not able to prove it when asked. So we'll go through it, that how simple the proof is, but how people are not able to figure it out when given the time also. So first of all, let's write what we want. Given f is differentiable at C means given that f prime C exists, and so the limit of h tend to 0, this expression f of C plus h minus f of C upon h. So limit h tend to 0 of the quotient f of C plus h minus f of C upon h, this limit exists. Exist means exist finitely. That goes without saying. Exists. So that is your f prime c. That is the meaning of f is differentiable at c. You want to prove that f is continuous at c, means you want now from here you want to imply that limit x tend to c, f of x is nothing but f of c. This is the definition of continuity. So you want to prove that if f is differentiable at c, f has to be continuous at c. In fact, I can rewrite this definition as I can set x equal to c plus h, and this will transform as limit h tend to 0 f of x is c plus h is f of c. So in the language of h, I can write equivalently. This is equivalently. I can write equivalently that if f is continuous at c, it means that limit of h tend to 0 f of c plus h also equals f of c. Let's try to prove it from left to right. Now, consider limit of h tend to 0 f of c plus h minus f of c. Consider this one. If you consider this limit, then I can write it as limit of h tend to 0 f of c plus h minus f of c over h times h. There is no harm in dividing by h because as h tend to 0, h is never 0 because we know that h is not 0. The limit concept means that h can be as close to 0 as possible but never equal to 0. If you talk of c, then same holds for c also, that c is that x is as or rather x is as close to c as possible, but x is never equal to c, and that tells you that h is never 0, although it can be as close to 0 as possible, arbitrarily close. Now it's like this one. Let me change a color one more time. So it is like this one, that there are two expressions, so call them say a and b. So now what you are doing is that you are asking this one, how does one deal with limit ab? So limit of some function, some numbers, limit of product of two expression. Now we know a result that if individually limit of a and limit of b exist, it means that limit of product becomes product of limit, and so we can write that this is just limit of a, appropriate variable must be here, and limit of b. Means if the limit of a and limit of b separately exist, then limit of product ab also exists and equals the product of limits. So this is expressed as limit of products. Limit of products is product of limits if the limits exist, which is the case here, because this a is nothing but f prime of c, this limit that we know it exists, so finite. This h, of course it is 0, so I can write this next step as that equal to limit of h tend to 0 f of c plus h minus f of c upon h times limit of h tend to 0 h. This limit is given to exist because f is differentiable at c, f is derivable at c, and this number is just 0, and so my answer becomes 0. Now let's go back. We started with this one, so we have proved limit of h tend to 0 f of c plus h minus f of c equal to 0. I can separate the limit, so I can write limit of h tend to 0 f of c plus h is equal to limit of h tend to 0 f of c. As this limit exists, because it is just f of c, there is no h over here, this is just f of c, So it means we have proved that ultimately limit of h tend to 0, f of c plus h is f of c, thereby proving that f is indeed continuous at c. So we have proved a very fundamental result, that this result is this, that we have proved that, let me go back and show you, that we have proved that if f is differentiable at c, then f must be continuous at c. This implies this statement x implies statement y. Now, to do this, we started with definition of both differentiability and continuity, and then we had got the property of limit that we used here. After writing like this, we expressed this as product of two limits, and we said here that limit of product is product of limits if both limits exist separately, which is the case here, because if limit of h tend to 0, this limit is by definition f prime c, and this is of course trivial, this is 0, and so both limits do exist separately, and so limit of product is product of limits, but that is 0 because one term is 0, and this is of course finite. This is finite, and if this is finite, this f prime c is finite. That's the meaning of limit exists, f prime c exists. And so we get limit of f of c plus h minus f c is 0, and in the last step we are getting this number, that limit of h tend to 0 f of c plus h is f c. And so it is proved now that f is continuous at c. The converse of course is not true. The converse of course is not true. Converse means if f is continuous at c, if f is continuous at c, implies f is differentiable at c is not true. If something is true, then I have to prove it. If something is false, I just have to give what mathematicians called a counter example. So one counter example is enough to destroy a claim, but hundreds of examples would not suffice to prove a claim. So to prove and to disprove. So to prove a result, you can't give examples, you have to prove it indeed. To disprove something, one counterexample is enough, means one example that will demonstrate that the theorem does not always hold. So here I will give an example of simple one. Fx is modulus of x. We can prove geometrically also and analytically also that f is continuous at all points. In fact, the graph looks like this. So we know that this f is continuous everywhere, even at this point also. In fact, it is f of x is x greater than equal to 0, and this is minus x less than 0. The only point where it may fail to be continuous was suspect point was x equal to 0. That are the suspect point. But we quickly find when you write limit h tend to 0, f of c plus h, and limit h tend to 0, f of c minus h, both h is positive. So this is like left hand limit, this is like right hand limit. If you find both happen to be 0, and so we say that this function is continuous at 0, everywhere else it is continuous. But this function is not differentiable at this origin. That we can test analytically, and that we can say that suppose we write f prime plus 0, which is notation for right hand derivative at 0, and similarly we have got f prime minus 0, that is called left hand derivative at 0. So we can write f prime plus 0 is limit of h tend to 0, f of 0 plus h minus f of 0 over h, and of course h is always positive. Limit h tend to 0, f of h minus f of 0 upon h. So limit h tend to 0, if f of h means that it is h is always positive, h is positive, so we'll go back to this one. This is still h, so we can write this is h, f0 is 0, and this is 1, so this is 1, so f prime plus 0 is 1. If I calculate f prime negative 0, I will get limit h tend to 0, f of 0 minus h minus f of 0 upon negative of h. This is important. Like if f primes, you want f prime plus f prime negative, if you want f prime this one at c, then you should write limit h tend to 0, f of c minus h minus f of c over negative of h. This negative comes because we should always take the difference in the order. So this is nothing but c minus h minus c, that is negative of h. So be careful of this negative. Once that is understood, we can go back and we can write again that this number equals limit of h tend to 0, f of 0 minus h, f of minus h. Remember, h is always positive. The derivative left hand would be taken care by writing 0 minus h. So minus h. So h is positive, minus is negative. We go back here. So minus h, it means this is negative of negative h. This is still 0 upon negative h. So limit of h tend to 0, h upon negative of h, and that equals minus 1. So we get that f prime, the left hand derivative of f at 0, that equals minus 1, and we already had f prime plus 0 is plus 1, and so we are seeing that f prime plus 0 is not equal to f prime negative 0, and so f is not differentiable at origin at 0. One more point about this problem, that because f of x is given to be mod x, we know that f is defined from R to R. So somebody can ask you that f prime. So tell me the domain of f prime. Domain of f is of course R, but domain of f prime need not be always R. Here we see that it is not R. In fact, f prime is, domain of f prime is R minus 0, and this R is alright codomain. And we can also define f prime x, that what is f prime x is like closed form. So we can write like this, that because f of x was x greater than equal to 0, negative x, x less than 0, my f prime x, because this is defined for all x, so in fact I can write this further as x, x positive 0, x is 0, and minus x, x less than 0. So I can write f prime x as 1 when x is positive, negative 1 when x less than 0, and at 0 it does not exist. It does not exist. So we already have taken care there by saying that the domain, and so f prime x is 1 when x is positive, it is minus 1 when x is negative. So we have also got a new function. You have got a new function f prime from f by some operation, and that operation is only called, it is differentiation. So we proved differentiability first, and then we found expression for f prime. So this is the domain f prime. So d of f prime is R minus 0. This is what we are doing. This is an important example. Coming next is, there is one more thing, that if f is differentiable, then of course f is continuous. Converse, we prove that not true. But the derivative but the derivative itself need not be continuous. So if f is differentiable, f is continuous, but the derivative, that is f prime, need not be continuous, because f prime is a new function, and it again must pass the test of differentiability as f does. It f prime does not inherit this property from f. That is, f is continuous, but f prime need not be. So we can take one example, that f of x, let us check what happens. We'll take 2 x sine 1 over x is not 0, 0, x equal to 0, and other is f of x is x square sine 1 over x is not 0, 0 when x equal to 0. So in both of them, just power of x is increased. In fact, one can go on and construct functions like x cube sine 1 over xn sine 1 over x, which are also really interesting function, and we study them a lot to understand some concepts of calculus. So here our objective would be to find the f prime x. So what I'll write, that we will write f prime x is, if x is not 0, then you see fx is product of two functions which are differentiable, because x is differentiable, and sine 1 by x when x is not 0 is differentiable. So we can apply the product rule and we can find its differentiation. So I will write f prime x is, so we are using this rule that uv prime is uv prime plus vu prime. So I'm writing x times cos of 1 over x times minus 1 over x squared and plus sine of 1x times 1. So I can write this one as f prime x is not 0. At x equal to 0, I don't know, because we have to find by something called first principle. So we have to use first principles, or say you have to use definition. You have to use definition. So we will write again what we found. F prime x is x cos of x. So this is minus 1 over x times cos of 1 over x and plus sine of 1 over x. If I want to find f prime 0, so I'll write f prime 0 is limit definition h tend to 0, f of 0 plus h minus f of 0 upon h, if this limit exists. If this exists, we do not know right now. So we'll write limit of h tend to 0, f of h, that is given to be h times sine of 1 by h minus 0 and upon h. So this becomes limit of h tend to 0 sine of 1 over h. Now this limit does not exist. How do you prove that? Of course, you can have a layman's idea by saying that when h tend to 0, then sine 1 by h, of course, it will oscillate very much, and sine 1 over h will not tend, to some definite value, and so limit does not exist. That's fine, but we can have other method that is good. What we will say, that we will create two sequences. Let's say that we choose xn is 2n pi. Xn is, let's say we choose xn is 1 over 2n pi plus pi over 2, a sequence, and yn is 1 over 2n pi minus pi over 2. So these are the two sequences, and when n tend to infinity, this sequence tends to 0, and even this sequence also tends to 0. So both these sequences tend to 0, that is, this 0 is here. So I can use what is called sometime sequential definition of limit. Means if you want to find limit of x tend to f of x, then you take sequence xn and yn. Then for all such sequence xn, yn, zn that tend to a, this means that limit n tend to infinity xn equal to a. That's the meaning of sequence tending to a. So for any sequence that tends to a, if you find the limit of function of that sequence, then that also tend to the same limit, then we can say that limit exists. In other words, if you want to prove that limit exists, it's not good idea because you have to check all possible sequences. But if you want to prove that limit does not exist, then you just select two sequences, you just think of two sequences, you just produce two sequences out of your imagination, that you just produce two sequences such that these both go to a, but limit of n tend to infinity f of xn and limit of n tend to infinity f of yn, these two are not equal, then you have proved that the limit of this function does not exist. We are applying the same thing here. So we have chosen for sine 1 by x these two numbers, 1 by 2n plus pi by 2 and 1 over 2n pi minus pi by 2. Now let me calculate limit n tend to infinity sine of 1 upon 2n pi over pi by 2, this one, and limit of n tend to infinity sine of 1 by 2n pi minus pi over 2. So I can get this as limit of n tend to infinity sine of, it was 1 over 1 of 2n pi by 2, and same holds for here also. So I can write 1 over 1 over 2n pi minus pi over 2. So this comes sine of 2n pi plus pi over 2. And here we're getting limit n tend to infinity sine of 2n pi minus pi over 2. So one gives you 1, other gives you negative of 1. And so that tells you these two are not equal. These two are not equal. And the conclusion is that limit h tend to 0 sine of 1 over h does not exist. This does not exist. This will come again and again. So pay special attention to this limit. But last time we did limit h tend to 0 h sine 1 by h. That is 0. This exists. That was by sandwich, because this sine 1 over h was bounded and this h limit tend to 0. So we are able to write that h sine 1 by h modulus less than equal to modulus of h and minus modulus of h. And because this all, they both tend to 0, so this limit also tend to 0 by using sandwich principle. So coming back to our example here, that we have got this one, that we can test this here, that you have got this expression fx was x sine 1 over x. You found that f prime 0 does not exist. Let's go back to this one, fx x square sine 1 by x, and then x cube sine 1 by x. When I take f of x is x square sine 1 over x is not 0, and 0 x equal to 0, curious thing happens. Here again f prime x is same. It is x square, this part, the same part like last time, cos of 1 over x by chain rule minus 1 over x square plus 2x times sine 1 over x when x is not 0. And then when you have here 0, we do not know x is 0 what it is. Last time function was there in which it was not differentiable at origin. This let us test by simple first principle. So write f prime 0 is limit h tend to 0, f of 0 plus h minus f0 upon h. That gives you limit h tend to 0, f of h minus f0 upon h. That gives you limit h tend to 0. F of h is this time h square sine 1 over h. So it is not single h, it is power 2. And upon h, that gives you limit h tend to 0, h sine 1 over h. And that answer is 0, as discussed earlier. So f prime 0 is 0. It means you are saying that this we know this is 0. So we can write this finding as this way, that f prime x is negative of cos of 1 by x. Let's check. Negative cos of 1 by x, x square cancels out, and plus 2x sine 1 over x if x is not 0, and 0 if x is 0. So you have found that f prime is now r to r. So f prime exists. Earlier it was, the first example was f prime was r minus 0. Now call it just gx for a moment. Now I want to find if g is, I want to find if g is continuous at origin, that is at x equal to 0. I want to test that whether g is continuous or not. So g is a new function. So what we'll want to write, that I want to find out whether limit x tend to 0, g of x, this number equals g0 or not. This is what I want to find. If this is true, then I will have proved that g is continuous at origin. Let us calculate limit x tend to 0, g of x. So if you calculate this limit x tend to 0, g of x, it's quite simple calculation. So we write limit x tend to 0, g of x equal to limit x tend to 0, g of x, that is minus of cos 1 over x and plus 2x times sine of 1 over x. Now you find that this limit does not exist, because although this limit exists equals 0, there is no x term here, nothing is here, and so this limit does not exist. This limit does not exist. It is nothing over here, and so this limit does not exist. And so we have proved that g0, of course g0 is 0, but limit does not exist, and so we have proved that this function g is not continuous at origin. So the function f was of course continuous at origin. We found f prime. G is not continuous at origin. If you take the next level, then that will tie up all the things. So fx is x cube sine of 1 over x. X is not 0, and 0 when x equal to 0. In the same way, I find now f prime x equal to x cube times sine of 1 over x. I can write as cos of 1 over x and times minus 1 over x square plus 3x square times sine 1 over x when x is not 0. And at 0, we'll again find f0 is 0. A quick calculation is this, that f prime 0 is limit h tend to 0, f of 0 plus h minus f0 by h. So that is limit h tend to 0, f of h minus f0 by h. That is your h cube sine 1 over h upon h, limit h tend to 0. Like last time round, you have got limit h tend to 0, h squared sine of 1 over h, and that equals again 0. So you have seen that as long as there is something to go with sine 1 over h, some power of h, positive enough, no need to be integer. So it means these kind of thing, h square or even root h, they will all go to 0, 0, 0. So f prime 0 is 0. So this number is 0. I can again write f prime x by simplifying a bit. So f prime x is, here we have got x square cancels. I have got minus x cos 1 over x. So minus x cos 1 over x plus 3x squared sine 1 over x when x is not 0. And when it is 0, obviously it's not defined at 0. When x is 0, this is 0. So we have found that this f prime is defined for whole R, and f prime is like this. Let's call this function kx, and let's find out whether this function is continuous. We ask ourselves the question, continuous at origin or not. Again, it's a new function. It must pass the test of continuity if it is to be continuous at origin. So we calculate limit of x tend to 0 kx, and we'll compare with k0. If they agree, these values agree, then we are done. Then they will be continuous. So limit x tend to 0, limit x tend to 0 kx will be limit of x tend to 0. Kx is this much. So this is minus x cos 1 over x plus 3x square sine 1 over x. So that gives you that now x appears here, which was not appearing until now. So now this is 0 and this also is 0. So our answer is 0. And we know that k of 0 is, of course, at value, you can see this k0 is 0 here. So k0 is 0. It means this function kx is, of course, continuous at x equal to 0. That is f prime x, that is a derivative of f, is continuous at origin. So let us go back and see that all things that we have started with x sine 1 over x, x sine 1 over x, x sine 1 over x. This function, of course, this function is not differentiable at origin, and so there is no question of this differentiability being continuous at origin because it is not defined only. So this function is not differentiable at origin, fx. When you move to x squared, then you find that if you go to x squared, you find that f becomes now differentiable to origin, and so f prime has got r to r. F prime is r to r. So it becomes differentiable at origin, but still f prime is not continuous at origin. F prime is, of course, defined at origin now because the domain is r, but f prime is not continuous at origin. Once you go to next level, x cube sine 1 over x, you find that not only f is differentiable, that of course was coming from x square also, so there is no improvement. So f is of course differentiable. So again f prime is from r to r, but this time the derivative itself is continuous at origin. So if you talk of this function x sine 1 over x, x square sine 1 over x, and x cube sine 1 over x, to summarize, and this is x is not 0 and 0, this is the common thing for all of them. 0 when x equal to 0, 0 when x equal to 0, 0 when x equal to 0 and x is not 0. In all of them, these functions, say let's call it f1, f2 and f3, you find that f1 is not differentiable at origin. f2, and so there is no question of derivative being continuous at origin because derivative is not defined only at origin. f2 is differentiable at origin, but derivative not continuous, means f2 prime not continuous. f3 you will find again is differentiable at origin, but this time derivative is continuous at origin. That is, not only f3 prime exists, f3 prime exists means the derivative does exist, and moreover derivative is itself continuous, and so we found that this kind of thing is coming up. So normally in JE you are asked the questions choices answer choices sometimes are that given a function f, they will ask you then this f is differentiable or derivable at this point, or other choice can be tricky choice can be derivative itself is continuous or not. So you have to test again. So this kind of example will tell you that derivative is this. There is one important step of that suppose sometime you want to find the relationship between derivative of f at c a point, so value of derivative, and limit of derivative of f at c. Means you want to explore that how does limit x tend to c f prime x and the value f prime c, how do they match, how do they agree, like what is relationship between these two, this versus this. So limit x tend to c f prime x and versus f prime of c, you will find this one that if limit x tend to c f prime x, if this limit exists means exist finitely, that goes without saying, but to stress or to make myself more clear, I'm writing finitely. In fact, JE also writes exist and sometime in bracket they will write finitely. So it means they are just trying to assure you that if you thought of infinite things, then be warned. In bracket, I have put finitely. So if f prime x is finitely, if this is the case, then this only will be the value of f prime of c. And in this case, actually, f of x, f of x, or derivative of prime x, this derivative is continuous at c. So if this is the case, that limit of x tend to c f prime x means the limit of derivative exists, then this itself is equal to the derivative of f at c, that is f prime of c. This part of theory will help you in finding f prime c quickly when you discover that f prime x limit exists. If it does not exist, of course we have different cases, but right now if it exists, then we are good because we can find f prime c very quickly. And related thing is this one here, that we already have calculated example that fx equal to x cube sine 1 over x was there this example, and x is not 0 and 0 x equal to 0. In this example we found f prime 0 was 0, and so here we can use, let me erase this in right again, so x cube in this example, because if you write limit of x tend to 0 f prime x, this existed, this exists here, we found this answer to be 0, and so it will mean that in fact f prime 0 is just the value, f prime 0 is the limit of derivative of f at 0, and this is nothing but this is value of derivative of f at 0. So you have learned that in some cases the value of derivative of f can be equal to limit of derivative of f at the same point, and in those cases the function f prime, the derivative itself happens to be continuous at the point in question, and so it happens like this. So today we have mostly covered theory. So today we have mostly covered theory, and tomorrow we will take up problems.